Hi, my name is Hennawy. I work for Johns Hopkins APL, and I was part of a team, a great team of a mission that we just launched recently, RBSP, and we were talking about, we are gonna talk about a topic I think it would be interesting for a lot of people, which is COTS integration. I believe that COTS is here to stay for a long time, and when that COTS paradigm was introduced early on, in the 90s, had a lot of promises. It delivered a good amount of it, but sometimes it's painful, and sometimes it's really painful. So here I picked up. So here I picked up a particular event that we went through in the development of that mission that I would like to share with you. I would like to share with you the mission itself, what we're doing, the system. I would like to share with you the issue and the cascading event of seemingly harmless event to something that will affect the mission and raise some flags. And how we went through our investigation, and then I think I would like to share with you our lesson learned, after action assessment of what we thought about how we're gonna improve it. COTS is here to stay. How we're gonna deal with it in the future, so it'll be, more delightful experience for us. So what we're building a simulation, a model and simulation for that mission, and that model and simulation have many customers. So actually, we're using it starting from development through integration, through IVNV. So IVNV is using this hardware in the loop simulation, mission simulation, and even after launches, we keep using this model and simulation. So it's a durable thing that we're building. It's high fidelity. It's real time. It's hardware in the loop. We're doing different configuration. We're doing fantastic things with it. Great team working on it, and the way that we're architecturing it. Do we have a pointer here? Okay. The way that we're architecturing, not sure that we're having a pointer. Oh, here we go. Okay. The way we're architecturing here, we're having a chassis that have a hardware platform, and we're having a real-time OS with a bunch of drivers on it. And then we have our middleware that we developed. That's our thing in here that will abstract drivers and OS, etc. And we have a real-time application. With that, we're having some interfaces, wrapping around the system, the hardware under loop of the system, hugging it, telling it what you are, how you're doing, what's the space you're in, instruments streaming into him. So we let the spacecraft that we're simulating feel that if I'm a spacecraft, I'm in 2018 and I'm doing that around Mars, for example. Nice system. Okay, so what was the issue? Just hangs. And so we're having a system, a fully functional system, a tested system. Everything is working fine. Runs for a month and just hangs. Nothing. No hardware interfaces. No that was a nuisance at the beginning. So we'll send somebody to the lab, to the simulation lab, and reset it, and everything is fine. That won't cut it with us. We have simulation. We have long-time simulations. We'd like to do before launch simulations of many, many days of the life of the spacecraft to do things. And we cannot hang in the middle of the 5th day. We got all these people, and we're doing a launch sim or maneuver or something like that, and we've done a maneuver 4 days in the middle, things are gone. We cannot. So we got to solve that problem. We're gonna figure out why that thing is hanging. So that little nuisance became like, an issue, project level risk. What are we going to do? That's our problem. That's our project. What's our approach in here? So our approach is, okay, basic questions. We got hardware that can fail. We got soft OS that can fail. We got drivers that can fail, and we got our application that can fail. So in each one of them, we decided to, analyze. And when I'm talking to, actually I'm going like, here like, in sequence, but we didn't do it in sequence because, as I told you, it's a hard problem because it's happened every week, every day, every month, in the middle of the night. You don't know, right? So it's like, you're having a window of opportunity of like, capturing some data when it happens. And you need to do as much as you can in tandem in all of these levels. So what we came up with is that we're gonna investigate the hardware. So we have hardware, so like, hardware, like, investigate the synchronous and the non-synchronous size of the hardware, interrupts, timers, the synchronization of the timers. So we start like, looking at the timers of the system. We start looking at like, what's our interrupt structure? What's our interfaces? So we looked at like, because I mentioned to you that's a chassis backplane PCI, so looked at our PCI architecture in here, like, who's feeding us, who's talking to us, who's interrupting the OS, or who's interrupting our application. And, the synchronous timers and what's happening on the timers and ticking and all that kind of stuff. And we looked at our software, so we decided to say like, okay, what's inside of the software? We have interfaces that we can stress, and we have components that we can really work hard. So we're having like, outside thing that can talk to us, so we can like, talk to it from like, our Ethernet interface, our PCI interface, our serial interface, and let's hammer it with different things. Let's hammer it with wrong thing, erroneous things. Let's jitter it. Try to get something out of, try to make some observations, try to do some analysis. So we identified our external interfaces, and we really like, build a nice test, stress test suite. And we worked our internal mathematical models, like, really crank it up. We did like, fine things with it. We increased okay, and we haven't only done that in our, base system. Okay, we said let's take that system, let's take that software, and put it in a different environment. So let's abandon the chassis. Let's put an OS, that same OS. Let's put it on a regular PC and our application, and just like, stub our drivers to dump. So we don't have a hardware in the middle. So we have like, different different combinations and permutation of the system working. Try to observe like, what's going on, and that's a chart here, like, when we were trying to analyze the PCI structure, going into the single board computer that we're dealing with. Beside that, okay, so we need to develop some tools. So we developed some tools beside like stressing our software and like, going through verify like, static analysis of like, with these great tools that people are using it. Let's build some tools that will capture data, tools that will do some visual or audio or textual feedback to us. So we build like, all of these tools that's running in the background. So like, if the application is not running in the background, if it's not running, we're gonna run this. And we did another drastic measurement that we shut down the application itself. We just let the OS run with the hardware, and we ran these guys. So assuming that our application, it's a perfect application. Let's assume that. But there's a problem with the OS itself, interacting with that hardware environment of it. And as I mentioned to you, that we start looking at, well, I had here beside this chart, I have another one that describes the hardware tool that we use. So we start we start investigating the hardware level of bringing PCI analyzers and let them in, and come out with different probes on the PCI bus. It will trigger when something happens. It will trigger when that interrupt happen, or the combination of that interrupt and that interrupt happen. We came up with hardware in the loop analyzer for the OS. So it's kind of people are familiar with ICEs or the JTAG. We're analyzing the hardware with the OS in the same time, so we can trap on something. So these are, so we build software tools, we build hardware tools, we build stress tests, and we start talking to vendors. So we talk to vendors, first I can run around the vendors with the vendors as okay, we'll open you a ticket. I think everything is fine. I think do this and do this and do that, and you go through the active list. And then we went to high support level after that, because all of these measurements failed. We're doing the right thing. We're operating a good OS and a good board with good software. And hey, you guys, you want our software? Okay, here's our software. Looked at it, software perfect. So everything is perfect. So went into kind of high-level discussions with the OS vendor and the firmware vendors, and then they asked us to to play with the frequency of the OS, how the OS is ticking, the tick rate of the OS, and we discovered that it's halting faster. So it was an epiphany. One of their engineers came out with probably it's an idle loop, and we've seen that because we build that JTAG hardware in the loop, and we see when it hangs, the last thing before it gave up the ghost, it's just sitting on halt instruction, just milling on halt instruction. So something happened that it's just decided to give up. So they instructed us to rebuild the OS with no halts. So we'll avoid these halt instructions. They have this in their OS. And it worked fine. So something is halting the system. And that's a Band-Aid. It's not good enough for a space mission. Another program, we got it not to halt, so that's fine. But we need to understand the root cause. Why it's halting? When we rebuild the operating system differently, it's misbehaving. So we discovered that hey, some of our test beds don't halt, and some of them do halt. So we went to what's the difference between that and that, and went and read all the OS document, release notes and errands. Firmware, release notes and errands, and the hardware too. And we discovered that we have different minor hardware revisions of the board that we're using in some test beds and other test beds. And that causes the issue, because test beds never hang and the other ones hang. So obviously there's a difference between them. And we discovered the difference that they have different bias. So I'm having the same thing, but I'm having different bias. So what's the difference between that bias and that bias? We went to the chip manufacturer, which is we went to the chip manufacturer of the CPU manufacturer release notes and errands. And apparently they built a chip, they built a CPU with an error in it. And that error, that's in the CPU level. So I will show you how that impacted our mission. So that CPU error was supposed to be, of course, you build all of this, lots of CPUs. You'll not throw them away. They will be sold in firmware and BIOS. That didn't happen. So that BIOS that was running with this operating system was good enough, but for a lot of people, but not good enough for people like us, who do this kind of missions. So they didn't have it in their BIOS, and the operating system was handling that in an ungraceful way. So we're having cascade of three things. We're having three COTS right now. We're having a hardware, we're having a firmware, and we're having an OS. That they're not playing good together. So each one of them is fine, but the three of them together in that particular combination is not fine. Ouch. So we talked to them. We talked to the BIOS manufacturer, and they claimed that their BIOS is up-to-date, and they updated after our various conversation with them. They updated their updated BIOS to another updated BIOS. So it's not quite updated. But it was solved, and actually we discovered that there is a Japanese company that came up with the solution for it that nobody picked, Toshiba. Okay, and that was sitting there in their, so apparently they ran into this problem. So that's the root cause, and we solved that issue. Lesson learned. How can we get better out of that? That's a hard problem. I ran into a lot of cost issues before, but this one was tough, and we would like not to get more of this. We'd like to use COTS. We'd like to cut costs and be competitive and be on budget and offer good solutions for our sponsors. Well, we discovered that we've done good things. We liked our stress tests. We think that we should go with any product to stress it. We'd like to think about pre-hand on stress tests that we can use. We'd like our software tools that we have. It's a good idea to when you're not doing something with your system, you can have a software tool that will exercise things in the background and get you value added, and you mature it from mission to mission and from a project to project. We like our hardware tools. We thought that these are bread and butters, and we should be very comfortable with them, using them in different configuration that we'll pick up with our system. And the final thing, we'd like to understand what we're buying more, and that's the key thing that we need we decided that we're going forward. It's not enough I'm reading a data sheet of that board is working in that operating system, that RTOS. It works with RTOS 1, RTOS 2, RTOS 3. No, we'd like to know more than that. We'd like to know what kind of configuration of that board. Is it workable with that RTOS, or it worked with that RTOS? And who used it? Which is not bad. It's not bad or good. We're just I would like to understand that, I'm the first person putting the operating system on that board or on that PC, or I'm the first person using this kind of combination of things, so I can have a risk. And that's the gist of my our last slide in here. If I'm having a big mission and I don't want to bother doing that fantastic job of troubleshooting and figure out stuff that overall COTS manufacturer will do, and I will do another fantastic job of doing my modeling and simulation I'm good at, versus investigating all of this. I will get an integrated cost solution. If I cannot, that can be a lot of money sometimes. If I cannot afford that, I need to understand what I'm buying, and the combination of COTS together, and assign them a risk, and integrate that risk with as we go along. And also we discovered that we'd like to, like, if I'm introducing a new technology with my engineers, so like the human factor to it, so like if I'm introducing that, that new system, that new operating system that a lot of people are using, that other operating system, so they're more comfortable of like working with it than this one, and it's a better operating system. But I need to assign some risk to it, and when I'm moving into my mission, I need to, to update that risk. So we'll have like a better understanding of how we're dealing with the cost. We're very good at like developing software, our software, but I think like we need to have like another like in tandem kind of stream of how to integrate our COTS with software, and like deal with them in the life cycle of the COTS as the same as the software life cycle. And that's our conclusion. And we got 4 minutes for questions.
Earlier in your presentation, you said that you increase interrupt rates in order to perform stress testing. And I was wondering, can you give a little bit more detail about that? Are you talking about interrupt rates, say, from like another PCI board that might generate a PCI line interrupt? Or are you talking about some internal interrupt too, or something more under software control, like say setting a timer?
Okay, so we fed PCI interrupts in a higher rate than the regular PCI interrupts that was coming from our regular boards. So we have like a chip that will FPGA that will just, we can like have whatever waveform. So that's the asynchronous, and the synchronous is like we, basically the clocking. We tamper with the clocking, and that causes this kind of interrupts.
So you make minor modifications to the hardware?
No, I didn't make any minor modification for the hardware. From the other side of the PCI bus, I just put an FPGA, and the FPGA I can program with whatever.
Oh, I'm sorry, I worded that wrong. I mean, by changing your FPGA, yeah, some people consider FPGA hardware. Okay, I understand what you're saying.
No, that's outside of my system. That's the other side of the PCI bus. So you're having a PCI bus in here, and that's your system that you're testing. And instead of like I'm having my regular board issuing a PCI like cycles and stuff like that, I have a different board that I can
All right, thank you.
You're welcome.
Oh, I was just going to ask one more thing on that interrupt rate topic. So when you stress test a system, and how do you come up with what rate you want to stress? Do you look at the spec? Is there a spec that says this is like the maximum rate this can come in, or do you take the approach of I want to see what software does if the rate comes in at some arbitrarily high level?
Good question. So like for my application, I know what my specs are. For the OS, I'm talking to the vendor. I'm telling them like how much you want me to stress that one, or how much you want me to stress your PCI interface or something like that. So I'm getting my feed from the people who are building it. They have their specs, so I'm getting their specs. But my stuff, I know like I need to operate on that serial interface with maximum amount of that amount of data rate. So I will do that.
So I'm the RTIMS maintainer, so I can tell you about this problem. It's a real old problem.
Mm-hmm.
It happens on both scales of the hardware. There's one side in the really low volume custom stuff where no 2 times you order it, you actually get the same thing because they're not built until you manufacture it. So somebody's done some custom FPGA, and this week it's this version, and next month it's another version. But the other end of that is what you see. They're actually, I've seen that particular bug that's kind of odd bug. The other one, there are some where that cascaded interrupt is actually broken in the interrupt controller and it sticks on. And the other extreme is they're so low volume that no 2 of these are alike because they're manufactured one at a time. And the other side is, unfortunately, the reality is there's so many variations that no one, not even Linux has ever, or Windows, has really ever run on every combination of those particular. You can get unlucky.
That's right. And we know
you may be the only one in the world who's running that hardware configuration, even in high volume.
and we'd like to know that. We'd like to know that. We'd like to understand that.
It's really hard.
And we go on understanding that. So like, you know, we'll have like a different attitude than these things work together.